Swayam Prabha. Digital India. Educated India.
So we can essentially define it with respect to the efficiency of a Carnot engine. So we can use that. Of course, we'll have to use some information. Now is that can we use the efficiency of a Carnot engine to define the temperature rather, and so now using this idea, we can see that we are now no longer relying on the properties of the substance, of a substance. Okay, so that's the basic idea. And let me again pause because we have talked about a few ideas here by now and see if there are any questions.
Sir, in the previous slide, what was the point about the second law? I did not understand that.
The second law is getting clarified in this next slide that I'm talking about here.
Okay.
Okay, so here we are defining something which is not based on the absolute properties of a, or which is not based on the properties of a substance. It is going to be something which is defined based on the efficiency of a Carnot engine now. So first of all, let us look at how this is measured in practice. One can construct a thermometer, and this is an ideal gas thermometer where we have a bulb where some gas is there, and then this is a liquid, maybe mercury is typically used. This is a manometer that you would recognize. And if we heat up this gas in the bulb, or this, that means that this bulb is experiencing a temperature which is different from the ambient temperature, then of course there will be a difference. The gas will expand, exert pressure on one side of the limb, and of course the mercury would rise in the other limb. Okay, and then we can measure this H, knowing, and rho gh is the excess pressure that we are finding, and this excess pressure can then be related to the temperature using the equation which has been given here. So you can see that I am now using the pressure of the triple point. I'm using the fact that at the triple point, my temperature is 0.01 degrees Celsius, which means 273.16 Kelvin. And then I am measuring the pressure, which is nothing but rho gh, and everything else we know other than h, which we measure from this instrument here, and then we get our p, and therefore we can get what is the temperature here. So this is what is happening. So this is, I mean, in practice, use the absolute temperature scale yet, which we are going to do in the next slide. But I'm just giving you a sense of how one can measure. Once we have this absolute temperature scale, how can we measure things using this ideal gas thermometer? So going back to the idea of a Carnot engine and using the efficiency that we had earlier. So we are going to consider again two temperature reservoirs. Now we are no longer sort of using it as heat and work. We are going to use it in trying to define a temperature scale for it. So let us say we have two temperatures reservoirs T1 and T3, and I introduce another reservoir T2 in it, in between these two temperature reservoirs, such that T1 is greater than T2 and which is in turn greater than T3. And then I connect a heat engine, a Carnot engine between these two reservoirs, another engine between these two reservoirs, and one engine which connects directly between the T1 and T3. So we are talking about three Carnot engines like what has been shown here. All of them take certain amount of heat from the higher temperature reservoir, reject certain amount of heat to the lower temperature reservoir, and the difference is converted into work. So by now we know that the efficiency can be written as 1 minus QL upon QH, which is only dependent on the temperatures which we have. So this is something that we have seen now, and this is what we are going to use for defining things further. Since efficiency is only a function of the two temperatures, we are going to say, so we can see that from this equation now, we are saying that QL minus QH is a function of TL and TH. Okay, so we are saying that Q1 and Q2 is a function of T1 and T2, Q2 upon Q3 is a function of T2, T3, and so on. So these are the statements that I can readily write. And then because I know that Q1 upon Q3 is nothing but Q1 upon Q2 into Q2 upon Q3, I see that the psi of T1 comma T3 is nothing but psi of T1 comma T2 comma psi of T2 comma T3. Okay, and therefore we conclude that whatever is this function here, this function have to be now written in this form. Okay, it has to be some function of T1 upon some function of T3. Okay, that's how I can write out this function I. Otherwise, I cannot satisfy this constraint here. Okay, so this is essentially what we are getting from our previous argument. Okay, so this argument, this sort of a picture is helping us to write out a statement like this. And this statement is further making it clear that we have to write out our efficiency or our this xi function as a function of T1 upon the other function here. There is no other way out. Okay. Now that means that now a choice. Okay, so before I move ahead, because this is one line of arguments, and then we will make another argument, another set of arguments in the next slide. Any question here?
So how can you conclude that it has to be of the form f of t1 by f of t3? It can just be something subtracted by something.
But then how will you satisfy this?
So let it be arbitrarily a of t1 minus t2 psi. Then if psi t2 comma t3 be a into t2 minus t3, then
See,
t2
your
t2
function
again
has
gets
to
cancelled.
cancel. Whatever you are writing, it has to cancel. If you take it as T1 minus T3,
So,
okay,
sir, it
this
can
will
be
become T1 minus T2. Let me just finish. T1 minus T2, and this will become T2 minus T3. So then this T2 is not cancelling out.
sir, can it be exponential of t1 minus t2 and t2 minus
Yeah,
t?
so that will be in the next slide. So I'm just pausing here because this is one argument. Now, what function we choose, that's the next statement. That's my next argument. But are we clear that this is the only option that we have first?
Excuse me, sir.
And yeah.
So can you just once again say what is the definition of psi T1 T2? Like is it 1 minus QL by QH or QL by QH? Because afterwards like you have taken
Yeah,
Q1
you are
by
right. Actually, there is again. I mean, this is also what you are saying is right. So essentially, I'm only so this is one minus. So if you want to write it, be more careful. It is one minus I of this. So xi is I'm just writing it as QL minus QH only. Okay.
Okay, sir. Thank you.
So if you want, I can just correct this as one minus. Any other question while I just correct this?
Yes, sir. We are using this Carnot cycle for calibrating the temperature. So, but what we were using that ideal gas thermometer for?
Further, we are going to define a temperature scale right now, and then we are going to measure the temperatures using this temperature scale. Okay, we need to have both the things. We need to have a scale against which we are going to do. I mean, we are defining things first, and then we are going to just defining it unless and until we can measure it is no use. Okay, practically we can never use it. Okay, unless and until you can, I mean, actually calculate things or do things, right? So we are actually measuring things using this ideal gas thermometer.
Okay, sir.
Okay, so now as we said, so I'm assuming I'm moving ahead. So as was given, we could have an exponential function. Okay, okay, but we chose a simpler function, which is just th. Okay, so f of t1, let us just write it as t1, right? Why complicate things? Okay, we could have written exponential functions, but we have just chosen it as th upon tl. So it's just a choice now. Okay, so we can see that my efficiency now is turning out as 1 minus tl upon th, where now I have now chosen that these are now my so-called my absolute temperatures, And once, of course, I have chosen, I cannot just keep changing my definitions after that. So the efficiency of a Carnot cycle essentially becomes 1 minus TL upon TH. So we are now concluding now a couple of ideas. So we have saying that Carnot efficiency is now becoming 1 minus TL upon TH. And no engine can have an efficiency which is more than this. And we are also saying that we have now introduced, in the process, we have now introduced a temperature scale. And we've also introduced a way to measure our temperatures, absolute temperatures. So this is essentially what we have covered. This is what we wanted to cover before the mid-sem. So this is my last slide before the mid-sem.
Excuse me, sir.
Yes, please.
Sir, so we have defined the efficiency in terms of temperature for the Carnot cycle, but like how do we decide the scale in like the range in which this is acting? For that, we'll have to know the efficiency, actual value of the efficiency, right?
Correct. That's right. Yes.
So is that the same for all Carnot cycles, or like it will depend from temperature
So
to
Carnot,
temperature?
the answer is given right here, no, in front of you. It is dependent on the two temperatures between which you are operating the cycle.
Yeah, so how are we defining, like how have we completely defined the like temperature scale?
So we are defining it in terms of the thermodynamic, in terms of the Carnot efficiency. So here we are saying if I know eta, then I know these temperatures. So
Okay,
instead
sir.
of see again, we said that we are going to need certain information. Earlier we needed information of the properties of a substance. Okay, now we are defining it, basing it on the efficiency of the Carnot cycle. Okay, the only advantage that we see here is now it is not dependent on the substance. Okay, it is only dependent on the temperature of the reservoirs, and therefore this is slightly, hopefully, if you think about it further, because the substances saying that it is pure 100% pure substance, okay, this is going to be very, very difficult to get 100% pure substance. You can say that there will always be certain amount of impurity, and this impurity will come because the moment you handle it, okay, whatever you have a steel spoon on which you are keeping it, or you have a ceramic substance on which you are keeping your other thing, your substance which is very, very pure, can not some of these molecules of a ceramic or spoon get into from the surface on which things are kept, or the pure substance is kept, to your substance itself. Okay, and when you're talking, is it 100% and so on, and will that change the properties of the substance, and will it affect my temperature scale? So those are the type of questions that you get into. So we wanted to get rid of that, saying that we are not involving any substance here. We are only involving a Carnot engine whose efficiency somehow we know. Or we can say that, okay, so we can see that always is going to be an iterative process. Okay, so we define, like, let us say, a certain temperature scale. And then we say that, okay, based on that, we can try to see if we can have a Carnot efficiency, which is going to be always this number. Okay, we can of course check it by taking different temperatures, and then of course Carnot cycle is an ideal cycle; it can never be constructed. But I mean, so the thing is that I mean, still it turns out to be a more useful definition, because we are not basing anything on the properties of a substance. We are essentially relying on a different sort of an idea, which is the efficiency of a Carnot cycle. That's how I would answer that.
Okay, sir. Got it.
So in the last part of the derivation, we took the ft is equals to t or e power t. How can we take them, or it may be possible that ft may be a complex equation in t?
Yeah. So coming back to this question, so we have, all we can conclude is that it will have this form. Okay, this is the form that we can argue, or this is what we have argued. Now, what ft I choose, that is in my hand, because there is no constraint that I can see right now, right? So I choose to take a simplest function, which is just say that this is t. F of t1 is nothing but t1. That's my simplest choice, and I choose that. And I'm never going to claim that it is not the only choice. But I'm choosing it because this is a convenient choice. Okay, I could have taken a square. Why not T1 square? Why not T1 cubed? Okay, why not fractional power of T1? So I have a lot of options. No? Infinite number of possibilities I have at this stage. But I just choose something which is convenient for me. And hopefully it will not be very different from whatever was there earlier. So just imagine that you have redefined your temperature scale and you have tried to make it more precise. Now suddenly I say that everything that you have done in this textbook, all of them have to be, all these problems have to be reworked because all those numbers have stopped making sense now with respect to the new temperature scale that has been. So you can see just writing a textbook is going to require so much more effort. And so if you have to now teach everybody and then all these industries, everybody has to start thinking, recalibrating the instrument and start working with a new set of charts and so on. Just imagine the amount of confusion that will bring in. So you cannot bring about a disruption. You just make about a small corrections. So the corrections which are brought about are such that whatever you were doing, now we have made it more precise. So as earlier you were working with freezing water and boiling water, now we are saying that don't work with that. Work with triple point and work with a slope which is now being given like here, like this equation here. Okay, this is essentially coming from my slope. This is this is now in absolute. So I've defined my absolute temperature. So I know what is the scale there, what is the slope there, and then I use that to get knowing the pressure, I'm now getting my temperature. Okay, so I have now defined something which is slightly better. And how did I define? Again, using this Carnot cycle efficiency, I've defined my absolute temperatures. Okay.
But on changing the functions, we will get different efficiencies, and we know that the Carnot cycle must have the maximum efficiency. Then in that case, wouldn't be affecting the other
So Carnot
hypothesis?
cycle efficiency will remain the same. That's the whole proposition. The efficiency of these two, because this is a physical temperature, no? You call it 200 Kelvin, you call it whatever 500 R or whatever you want to call it. Okay, this is also in some arbitrary units, it is some number. That number is for you, no? But the engine that you can operate will have a certain efficiency. You cannot convert more uh, than a certain amount of work for a certain amount of feed that has been taken in from this reservoir, right? So that is a physical constraint. Now, what temperature, what values you want to call it is up to you. So what will that change if you were, instead of taking a function like this, you have taken it as a square or an exponential? Okay, what would change is the absolute numbers, but of course this efficiency cannot change. Does that answer your question?
Yes, sir.
Okay, so let me just reiterate. In the next class, we will essentially have, this is going to be the last before the midsem. I will essentially wait for your questions to be there. Okay, so I will not have any material from my side to cover. Okay, or I don't want to cover start off with a new topic now. Does not make sense.